Now, let us give some queuing examples. Okay. Let me call this next level. So, introduction to queuing with some examples. Okay. Okay, so, in this is a course where we are going to encounter various type of queuing systems as and when appropriate. Okay. Now, I have to tell you what a queuing system is and what a queue is. Okay. So, a queue, we can think of queue as a so a queue consists of a server, okay, which provides some service, all right, and to that server there are arrivals, customer arrivals that take place according to some counting process. Okay. So, this arrival process can be arrival of customers, you know, to a ticketing counter, or arrival of phone calls to an exchange, or arrival of packets to a internet router, or any of these things. Okay. In all this, the server takes some amount of time to offer service to a customer. Okay. And when a customer is being served by the server, other customers have to wait for their turn, right. This is a feature that is common when you go to renew your passport, or you just call you know, customer service or your credit card or whatever, right. You tend to wait till your turn comes, right. So, this is you can see that this has widespread applications, and these counting discrete stochastic processes help us study various kind of queuing systems. Okay. So, as we study Poisson process or renewal processes or Markov chains, we will constantly be applying them to learn more about queuing systems. Okay. Throughout the course we will do many examples. Okay. So, in its simplest setting, we can think of a server, okay, and some sort of a buffer which stores awaiting customers. Okay. And arrivals occur to this queue as some point process, so counting process basically. Okay. So, this is time, and customers come in continuous time according to some counting process. Okay. And the server has takes some time to serve each customer. Okay. And this customers, so there is usually, if the server may be empty, which means there is nobody at the being served, or there could be somebody being served, and if somebody comes during the service interval of a customer, they will just queue up, okay, and they wait for service. Okay. Now, we have to think about what characterizes a queue like this. Okay. So, a queue is characterized typically characterized by the following. Okay. So, it matters what the arrival process of customers is, right. Right. So, if a lot of arrivals take place, you know that there will be a longer queue, right, and the statistical nature of this arrival process will obviously have some bearing on the statistical properties of how many people wait and how long you wait and so on, right. So, this is clearly important, an arrival process of customers is clearly important. Then the server characteristic, right, server which means how long does it take to serve a particular customer. Does it take a deterministic amount of time? Do I serve everybody in 10 minutes? Well, that is one possibility, but often it takes, that is also variable, right. So you may hold a call for longer or shorter. So, that is also often a random variable, right. So, the service time, so the amount of time that the server spends serving a particular customer is also a random variable, right, all right, and that random variable also will impact the the evolution of this queuing system, correct. Of course, there could also be serving discipline, service discipline. So, in some situations you may serve, I mean the logical way to serve in a queue like this is to serve the person who comes first, right, first come first serve, but not all systems work like this. Okay. Sometimes you may serve the last person who comes in, sometimes you may serve all existing customers at the same rate, right, all these possibilities exist, right, that also matters, right. Although we will study first come first serve. So, we will probably study first come first serve, last come first serve, there are other disciplines like processor sharing and so on. Okay. But I think this, when nothing is specified, people usually assume that this is for first come first serve. Okay. What else matters? The number of servers could also matter. Okay. So, for example, there may be multiple ticketing counters, right, and you could just be queuing up here, right. So, they all serve different customers, this is like an airline checking counter, right. So, the moment this guy finishes taking in, the next person in queue will be directed to the server which just finished serving somebody, right. So, there is only one queue, but the number of servers is many, right. So, this could be some M server system. So, you do not have to have this picture where there is only one server, right, you could have multiple servers, but just one queue. So, this is common in call centers, this is common in airline check-in. So, call center, there is multiple people who usually attend these calls and you get routed to the first person who becomes free, you must have noticed this. You do not always get the same person, you know this, right, when you call your credit card or something, right. Good. Also, the number of customers who can wait, which can be called buffer size. Okay. So, buffer is a terminology that comes from the communication networks world, where in the internet routers you store a buffer up a certain number of packets in a router. Okay. But this could just be the size of a hall where you wait, or whatever, right, it could does not have to be a buffer in the sense of a buffer in the internet. Okay. So, this is buffer size also matters. So, if the buffer gets full, you are dropped. Okay. If your booking hall is full and you cannot even enter it, you will go away. Okay. So, these are, I mean all these things matter in the way the system evolves, right. So, queuing theory is a field by itself, all right, and queuing theorists have evolved a certain Python notation to talk about what a particular queuing system behaves like. Okay. They use a slash notation. Okay. So, the slash notation works like this. So, it goes like dot slash dot slash dot slash dot. Okay. So, maybe here, so this talks about arrival process, okay, and the second one talks about service distribution in some sense, okay, which is item 2, service time distribution is what I mean. Okay. And this is the third one is the number of servers, and this fourth is the buffer size. Okay. All right. So, this is this will not make any sense to you unless I mean until I actually give you an example, right. By the way, this buffer size is optional. So, often you may not have the fourth dot, okay. You may just have 3, in which case the buffer size is assumed to be infinity, okay. There is no restrictions on how many people can wait, okay. So, often it is just dot slash dot slash dot, okay. The fourth one may not be there, in which case you assume that the buffer is infinite, okay. So, the most general is something like GG M n, okay. So, G denotes general, okay. Okay, it could be any general arrival and any general service distribution. Now, one potential scope for confusion is there are 2 G's here, right. Those 2 G's may not be the same. So, the arrival statistics, service statistics could be different, okay. Just because I say GG1Q does not mean that the arrival in inter arrival times or whatever has the same statistics as the service time, no, right. G just means general, and these 2 G's could be different, and of course, M servers and N is the buffer size, right. Usually some authors prefer to say when you have independent, right. So, when the service times across different customers are independent across customers, and the inter arrival times of the various customers are also independent, like in a renewal process. Some authors usually write GI, okay. To say general, you can have any distribution, but across users. So, you could have GI 1Q, which means that renewal arrivals, right, general but IID service times, okay, and of course, one server in this case, right. And I have not put a fourth slash, meaning that the buffer size I do not have any restrictions on how many people can wait, okay. So, GI1Q means renewal arrivals, general but IID service times across customers, and also an implicit assumption in all these queuing systems is that arrival process is independent of service process. What does that mean? So, the amount of, so the arrival time of a customer says nothing further about how long the customer will take for service at service, okay. So, for example, I cannot, so by looking at my arrival time you cannot tell whether I am going to be a let us say a big packet or a small packet in a communication network. Okay. So, it is usually in this notation gi1q means that the arrival process and the service time random variables are independent. Okay. I mean if they are correlated they could, I mean still a queue, it is just that this notation usually does not capture that scenario. Okay. Usually I should mention that the service discipline is mentioned separately. Okay. Usually not a part of this notation slash notation. So, you will typically say gi1 queue with last come first serve, right, okay, or first come first serve whatever queue, right. It is not included in this slash notation usually, and often when there is no service discipline specified you should assume first come first serve, just like when there is no buffer size specified you assume infinity. Okay. Oops. Okay. So, let me give you a few more examples of this notation. So, when I say MGI1 Q for example, this means memoryless. M stands for memoryless. Okay. So, in this case then MG1Q we have Poisson arrivals, memoryless arrival process, right, which is Poisson arrivals and general IID service times which are independent of arrival process. Okay. Yes.
Sir, should it be identical, like when I am serving the consumers, customers, should I always go in an identical distribution to the last customer whom I serve?
In this notation, right, when I say GIG or MGI1, the notation implies that the service times across these customers is independent and identically distributed. Okay. Sometimes some authors do not even use I, when they say MG1Q they mean MGI1Q, okay, but potentially they could be correlated, right, or they could even be non identically distributed across customers. This notation does not, MGI1 means IID across customers, okay, and independent of arrival process. It could be any distribution, but this is the same distribution for each customer and independent across customers and independent of the arrival process. That is what this notation means. I am not saying that this is true in all queuing systems, right. I am just giving some, see if you have the most general queuing system where everything is correlated with everything else is impossible to study, right. So, these are just examples of queuing systems we can do something mathematically about. Okay. The simplest queue mathematically is the so called MM1 queue. Okay. So, this means so this means both are memoryless, meaning that the inter arrival times are exponentially distributed as Poisson arrivals. So, this means Poisson arrivals exponential IID service times independent of arrival process. Okay. MM1Q means arrivals of Poisson, the time it takes to serve any customer is an exponential random variable, IID exponential random variable which is independent of the arrival process. Okay. All right. So, now you can make up stuff, right. I mean, now you can, what does M M N mean, right. Poisson arrivals, exponential service times, n servers. If I had M M N M, meaning the buffer size is M and so on, right. So, these you can talk about. What is a G, maybe I should write G I M 1, what kind of a queue is that? Meaning renewal arrivals, right, general identically independent identically distributed. So, this general renewal arrivals, exponential service times and one server, right, clear. So, this is how a queue is specified. Okay, I think it takes a little bit of getting used to, but once you specify these 3 things or 4 things across slashes, you know what you are talking about, right. And sometimes you may have to specify the service discipline.
Sure. MMN as in exponential service times across all servers also.
Correct. So, when I say MMN, so let me just when I say MMN, no matter which server the job goes to, the customer goes to, he or she faces exponential service times which are identically distributed across servers, okay, meaning that each server is working at the same speed. Okay. Of course, it is possible that the in a call center, for example, if you have a situation like this, yeah, so her question was that, so if you have MMN kind of a setting like this, you could potentially have one person in the call center who is more efficient than another person in a call center, right, in which case if you went to the more efficient person, you will spend I mean you will get out sooner, right. So, that is not captured in the, if I just say MMNQ, right, then it goes, I mean it is assumed that all the servers have the same service rate, service characteristics. Okay. So, it is not that these more complicated scenarios do not arise, in fact they do arise. All I am saying is that this notation does not capture those things, right. In fact, the call center example itself is a very important example. You want to know how to staff your, how much staff you put, right, for what kind of load. Of course, your staff are not identical, right, some are better than the others. So, just think about it, right, if one staff is extremely good. So, let us say this first person you have put in your call center is extremely good and is clearing jobs very fast. Most of the waiting jobs will go to her, which means she will be overloaded, right. So, you are penalizing her for working very well, unfortunately, right. So, these kind of problems do arise and these people have studied these kind of issues. So, if you want to study call centers properly, MMN where all the servers are identical is not, it is a good first order model maybe, but you should really be considering heterogeneous servers and all that, right. Good. So, all I have said is that there is some notation, okay, and when so from now on if I tell you what a MG1 or MGN is, you know what I am talking about, that is all. Okay. So, in this course we will study MM1, we will study a lot. Okay. So, this MM1 we will study a lot, MMN also we will study, MG1 we will study. Okay. GIM1 also I think I will at least have a homework, let us say. Okay. These queuing systems we will cover at some point. Okay. You could also have the number of servers could actually be infinite. So, what does that mean? There is no waiting. Okay. It is like having having a call center which is so overstaffed that nobody has to wait. Okay. So, that kind of a queuing system is also possible. In that case you speak of an M, let us say G infinity queuing system. Okay.
It's just like an arrival process.
No, it is an arrival process. No, the service process could be general. Okay. IID across customers, independent of service times. It is just that you do not queue up, you do not wait for service, you just spend time in service. There is nobody that you have to wait for, you as soon as you come there are infinitely many servers. So, you go to a server straight away, correct, but still you can talk about how many people are being served at any given time, right, clear. So, this is some sort of a limit m g infinity, some sort of a limit of m g n where n becomes very large, right, or m m infinity is some sort of a limit of m m n where n becomes very large, right. So, these kind of systems we can study. Okay. Is the notation clear? Any questions? See, generally if this notation, if there is something in the problem which says that the servers are heterogeneous or the service discipline is not FCFs or whatever, the problem or the exercise you are dealing with should say so. Okay. We will say, oh, last come first serve MG2Q in which the servers have different rates, we will say so. Okay. If you do not say anything, assume that buffer size is infinite, assume that all the servers are identical speeds and all that. Okay. And you can assume independence between arrival and service process always. Okay. And often this G I is dropped, usually people just speak of MG1Q or MG infinity Q, and it is assumed that the service times are independent across customers. Okay. In fact, I think Gallagher's book just uses MG1, MG infinity. Okay. So, as it happens, this MGI infinity is the queue that can be, so this can be studied using non-homogeneous Poisson process. Okay. So, the first Q we will study is the MG infinity Q, MGI infinity Q. So, the mathematically the simplest Q, the nicest Q is MM1, okay, which is exponential Poisson arrivals exponential service times. But to study is somewhat ironic, it is somewhat ironic that this is something that we will study towards the very end, okay, because we need to study continuous Markov chains, continuous time Markov chains before we can study MM1. Okay. But it turns out MG infinity can be studied just using non-homogeneous Poisson process. Okay. It is not the simplest queuing system in the from the point of view of its structure, but because there is a clever way to look at it using non-homogeneous Poisson process, you can, it turns out you can actually study it without doing any of these Markov chains stuff. All the other queues will involve some kind of a Markov chain, okay, which is what we will study towards the second part of this course. Okay.